Hi, I'm Mark Moses, and this is my CEDAR presentation on the observation and modeling studies of the effects of the 2017 solar eclipse on SuperDARN propagation. So, the eclipse in 2017 passed through the fields of view of the Christmas Valley radars and the Fort Hays radars. We ran them in a special mode on Eclipse Day, and so they only made measurements on the beams highlighted here, and they did a scan over the field of view in 1 minute, returning to the camping beam, which is highlighted in indigo for each radar, between successive beams. So those beams have the best data resolution. And this is these are the data from the camping beams of each radar: Christmas Valley West, Christmas Valley East, Fort Hays West, and Fort Hays East. In general, the top panels of a general SuperDARN RTI plot have operating parameters and conditions for the radar, but I've also added this one here, where which shows the distance of the eclipse center from the radar site. So it sort of serves as a proxy for eclipse magnitude. And the bottom plots show the colors indicate different parameters, such as the signal-to-noise ratio, velocity, and spectral width. The y-axis is radar range gate, and the x-axis is UT time. So, as you can see from all of these, around totality, which is about here for Christmas Valley and here for Fort Hays, there's a decrease in signal, or the amount of backscattered signal. You don't see a strong effect on the eastward-looking radars, but for the westward-looking ones, around leading up to totality, you can see an increase in the slant range of the remaining scatter. However, though it's at Christmas Valley, it's symmetric about the point of closest approach. At Fort Hays, the recovery is not exactly symmetric with the point of closest approach. Also, it's important to note that the low spectral widths and low velocities of all these data indicate that the majority of observed scatter is ground scatter. Christmas Valley West also had elevation angle data. This is, the plot here is from Christmas Valley West, beam 11, the camping beam, and we can see that the round leading up to maximum eclipse, there was a sort of a decrease in the elevation angles, or really only scatter from lower takeoff angles returned close to the point of maximum eclipse. So some of the questions we had from these data were if the increase in path length observed by the western-looking radars were due to changes in the altitude of peak plasma density, or due to ducting of the signals through the depleted region of plasma. Also, why the data from Fort Hays and Christmas Valley appeared to be so different. So to answer these questions, we had to do some modeling. So we modeled the eclipse as a 4-dimensional scaling of the EUV flux input into NRL's SAMI3 model. We then would ray trace through the output generated by this eclipse SAMI model using the FallLab toolbox, and to generate simulated SuperDARN data to compare to measured SuperDARN data. So just to give you an idea, the side profiles of the ray traces are for Christmas Valley West beam 11 as shown here. Top is the uneclipsed case, the bottom is the eclipsed case. Then the colors indicate the plasma frequency, which is related to the electron density. So we can see that significantly more rays escape from the eclipsed ionosphere than the uneclipsed one. Also can see that the range of the scatter increases significantly, but the altitude of peak electron density is about here, about the same. It's about right there. So this indicates that the rays are being ducted through the ionosphere as shown here, and this is the cause of the path lengthening, not a change in layer height. Now, this is an example of comparisons between the modeled or the simulated data and measured data. So here's the signal to noise ratio, and we compare it with the number of rays in each range bin in the simulation. And then this panel is the elevation angle that was measured on return scatter, and this plot is the initial elevation or takeoff angle of the simulated rays that reached the ground and did not escape the ionosphere. So you can see that there is a slight path lengthening in the modeled data, and the model also shows low elevation angles like the data. So the elevation angles are in good agreement. However, the magnitude of path lengthening seems to be a lot less than the measured path lengthening. So some phenomena associated with the ionospheric eclipse dynamics are not correctly accounted for. One such parameter that is probably likely inaccurate is the neutral wind. The SAMI does use the neutral wind in its calculation. However, the velocity of the neutral wind is obtained with HWM, and so it might not be an accurate representation of the neutral winds during an eclipse. So we did a neutral wind study to try to evaluate and quantify the effect that the changing the neutral winds in the simulation would affect the simulated SuperDARN data. So we ran these 4 cases of default wind, no wind, and only north-south winds and only east-west winds. We did these all in SAMI 2D as it was easier to iterate in that. Run a lot of cases quickly before going into the larger SAMI 3 model. So because it was in 2D and SAMI 2D is aligned along the magnetic flux tube, the simulated beams of the SuperDARN radars had to closely align with the local magnetic field declination. Also for this study, we used a different representation where we took the average path length of all the rays that reached the ground in the simulation and plotted it as a dot. Then took the longest path length and plotted it as an upper error bar, and the shortest path length and plotted as a lower error bar. And here are the results for both radar sites, Christmas Valley and Fort Hays, and the 4 cases. Now, you can see that the east-west wind in both cases appears very similar to the case of no wind, indicating that the east-west wind does not have a large impact on the eclipse response. However, the only north-south wind, or the meridional wind case, is significantly different from the no-wind case in both cases. You also notice first there are meridional wind from these results seems to have a greater impact on the ionospheric response than does the meridional wind. However, we also notice something interesting between the two sites. First off, the north-south wind and the HWM cases appear to be almost identical, even though however, the only north-south wind and the HWM and the full HWM winds actually appear very different in the Christmas Valley case, indicating that the zonal winds do play a larger role at Christmas Valley than they do at Fort Hays West, though less of a role than the meridional winds. So to understand why these features occur, we examine the drift velocity due to the neutral wind, so the drift velocity has three components, one parallel to the wind, one parallel to the field, and one perpendicular to both the wind and the field. And plotting each component as a function of altitude, because collision frequency and gyro frequency vary with altitude, we find that at F region altitudes, where most of the rays were ducted, the direct or field-aligned component is the dominant one at both sites. So magnetic field orientation will play an important role, and whichever wind is more aligned with the field should have a greater effect. Any variations in the wind that is parallel to the field should have a greater effect than the wind that is perpendicular to it. Now, looking at the declination of the magnetic field at both sites, you can see that Fort Hays is much closer aligned with north than Christmas Valley is. And they're about 10 degrees off from each other, even though their inclinations are almost the same. So this difference leads to the north-south wind having to the Fort Hays being more sensitive to changes in north-south wind than Christmas Valley, because Christmas Valley also has a slightly more of a east-west direction than Fort Hays does. And you can see that in just the calculations of the ion drift velocities for variations in the zonal wind, which is on the x-axis, and the meridional wind, which is on the y-axis. And see that Fort Hays, if you pick a certain meridional wind, as the zonal wind is varied, Fort Hays varies very little, but Christmas Valley grows slowly as the zonal wind is increased. In contrast, for the same zonal wind, both the Christmas Valley and Fort Hays drift velocities increase, with the increasing meridional wind fairly rapidly. Thus, this supports our conclusions that the meridional wind has a greater effect on the simulation than does the zonal wind. And this also shows that the magnetic field difference between the two sites is likely the dominant reason for the differences we observed at the two sites. But we should compare it with our measured data first. To see if we can find good agreements. And we find, so here the SuperDARN data is plotted in green in the same manner as the ray trace data, with the longest and shortest path lengths being represented by the error bars and the dot indicating the mean path length. And we can see that there is a gap between the two, between around total eclipse, like there is in these cases at Christmas Valley. However, at Fort Hays, see that in almost all cases this sort of increases. Maybe there's a teeny plateauing here, but the simulation mostly remains flat. In contrast, there is a significant dip here in the measured data for an increase and decrease. So we see that the slopes do not of the measured data does not follow the same trend as the simulated data. So more rigorous models of neutral wind velocity could correct some of these inconsistencies. So in summary, the SuperDARN radars in Christmas Valley and Fort Hays observed ground scatter during the 2017 eclipse, which increased its slant range prior to totality, what they return afterward, to normal conditions afterward, and a decrease in the amount of return scatter around totality. And the scatter was characterized by low angles of arrival. We created a SuperDARN ray trace simulator to evaluate different SAMI models and investigate the radio propagation during the eclipse. Using this tool, we found the path lengthening was likely due to signal ducting through the depleted plasma in the eclipsed region. And we validated our eclipse mask and determined that there was some other parameters that we needed to investigate. The neutral wind study showed that the ionosphere eclipse response is more sensitive to changes in the meridional wind than changes in the zonal wind, especially at Fort Hays. And it also confirmed a suspicion that the magnetic field geometry, the differences in magnetic field geometry, was one of the major reasons, or primary reasons, that the data from Fort Hays and the data from Christmas Valley appear different slightly. These studies also showed that we can use this ray tracing tool along with SAMI to understand eclipse dynamics, which hopefully will be useful for the eclipse in 4 years, which will pass through some SuperDARN sites as shown here. Thank you, and if you have any questions, you can contact me at the email here.